Welcome to another deep dive. This time we're going to be taking a close look at attention is all you need. This paper kind of blew up the world of machine learning when it first came out and introduced this thing called the transformer.
Yeah, this paper really changed the game.
And it's not just a bunch of tech jargon.
Yeah.
It's something that's having a real impact on how we use language with computers every day, like Google Translate.
Oh, definitely Google Translate.
And even these chatbots that are popping up everywhere that seem, almost human.
It's crazy how real they seem sometimes.
Yeah.
Yeah, these models, they're everywhere now. And, it's interesting. This paper kind of flipped the script on how we thought about language processing. Before attention is all you need, the go-to was something called RNNs. You can think about RNNs like a slow reader.
Okay.
Reading one word at a time, moving in a straight line through the sentence. But this paper asked a really interesting question.
Okay, what's that?
What if we let the model see the whole sentence at once? And that's where this idea of attention comes in.
So instead of reading word by word, the model can see the big picture all at once. So how does that even work?
Well, think about it like this.
Okay.
When you read, do you give the same amount of focus to every single word?
No, definitely not.
Right. You kind of skim over some parts. You zero in on the important stuff. You might even jump back to reread something. And that's kind of what these attention mechanisms in machine learning are trying to do.
Okay, I see. So instead of just reading everything like a robot, it's about understanding the important connections. That makes sense.
Exactly. And the really cool thing is why this was so groundbreaking, right?
Why was that such a big deal?
The old models, they really struggled with long, complicated sentences.
Right.
Like, imagine reading a whole paragraph and trying to remember the first word you read.
It's hard. I'd probably forget it.
It's so easy to lose track.
Yeah.
But with attention, the model can connect any two words directly. Doesn't matter how far apart they are. It's like it's drawing lines,
Connecting the dots.
Yeah, connecting the dots, highlighting the important links between them.
So it's like the model is making notes as it reads, underlining stuff, circling things. That's really neat.
Yeah, it's like it's actively trying to understand the text rather than just passively reading it. And you know what they called this technique?
What's that?
Scaled dot product attention.
Scale dot product attention. Okay. I think we're getting into the weeds a little bit now. What is that?
Well, it's kind of like a matchmaking system for words in a way.
Okay.
Each word gets this score based on how important it is in relation to all the other words.
So like a popularity contest for words?
Yeah, kind of. The higher the score, the more attention it gets from the model.
Yeah.
And the dot product part is just a way of measuring how similar words are to each other.
Got it. So it's basically saying, hey, this word's important. Let's focus on this.
Exactly.
Okay, but then I remember seeing in the paper they talk about multi-head attention.
Oh, yeah, good catch.
What is that all about?
So it's like, imagine a team of readers, and they each have their own special focus. One's looking for the subject, another one's looking at the verb.
Oh, okay. So instead of just one model reading the sentence, there's a whole bunch of them, like a team effort.
Exactly. And by combining what they all see, they can really understand the sentence on a much deeper level, like a bunch of experts putting their heads together.
It's amazing how they thought to do that. So that's all really cool. But, the real question is, did it work?
Oh, yeah. This wasn't just some theory. They tested it out.
Okay, so how'd it do?
They tested it on translating English to German and then English to French.
Okay, how'd it go?
It completely blew the competition out of the water.
Really?
Oh, yeah.
How much better was it?
So on English to German, they got a BLEU score. Have you heard of BLEU scores?
Yeah, I've heard of those.
Okay, so they got a 28.4, which is like 2 whole points higher than any model had gotten before.
Wow, so that's a huge improvement.
Oh, yeah. It was a massive jump. And they also did the English to French, and that BLEU score was 41.
Wow. So it wasn't just like a small little step. It was a complete game changer.
It really was. They basically reinvented the wheel with this paper.
That's incredible. And I'm guessing it wasn't just about making translation better. This paper seems like it had a much bigger impact, like on AI as a whole.
You're absolutely right. This wasn't just about one task. This paper changed how we think about language processing. The transformer, with its attention mechanism, it became the base for so many other innovations. It's like they opened up this whole new world, and everyone just rushed in to see what they could do with it.
Like the Big Bang of the Transformer universe.
Exactly. Like all these things we use today, chatbots, language models that can write poems and stories, image generators that can create art from text descriptions.
It all goes back to this paper.
It all has the Transformers DNA in it.
That's mind-blowing to think that one single paper could have that much impact on everything. Like they discovered some brand new element and it just changed everything.
It really did. It's like the oxygen of the AI world.
Yeah.
What's really remarkable, though, is the core idea. It's actually pretty simple.
Yeah.
They just took something that we do naturally as humans, paying attention, and made it work for machines. And it's a perfect example of how looking at the human brain can lead to breakthroughs in AI.
So cool. This has been eye-opening, and I bet our listeners are just as fascinated as I am and want to learn more about this whole thing. But before we go any further, let me ask you this. If machines can now understand language this well, maybe even better than we do in some cases, what does that mean for the future? I mean, what new things can we do, but what should we also be careful about?
That's the big question, isn't it? It's almost like we're on the edge of this new era. You know, talking to computers like they're people. We could do some incredible things, but we have to be careful too. Like, as AI keeps getting smarter, we have to make sure it's being used for good and not causing any harm.
Yeah, absolutely. That's a crucial point. Let's take a quick pause here to let that sink in. And then when we come back, we can dig into the nitty-gritty details of how the transformer works and see some of the amazing stuff that people build with it.
It's a really fascinating area, and I think this whole idea of attention, what this paper did was show us that there's a more intuitive way to think about machines and how they process language. It's not just about, you know, brute force computing power anymore.
Right.
It's about understanding like context and relationships and meaning, sort of like how we do it.
Yeah, it's almost like we're teaching machines to think more like humans.
Yeah, in a way.
At least when it comes to language. You mentioned before that this paper kind of ditched that old way of processing language with RNNs.
Yeah, they totally moved away from that.
Can you tell me a bit more about why they made that radical shift?
So RNNs, they were like the workhorse for processing these sequences of information, like words in a sentence. And they worked by going like one word at a time, moving down the line. But these authors, they basically said this whole step-by-step thing, it's holding us back.
Interesting.
And it made it really hard for the model to see those connections between words that were far apart.
I see.
And plus, it was just slow and computationally expensive.
Yeah, I can see that. So they were like, let's just scrap the old way and try something completely new. It's pretty bold. So what did they replace it with?
Well, they came up with this model that relies completely on attention. No more going one word at a time.
Okay.
And that's what makes the transformer so powerful. It can be trained way faster. It can handle these really long sentences without losing track of what's going on. And it can see these complicated relationships between words that we just couldn't capture before.
So they traded in the old clunky RNN for this like supercharged, efficient transformer.
Yeah.
That's cool. What kind of impact did that have on the performance? Like how much better was it?
It wasn't just about speed, though. It was also about how deeply the model could understand the language.
Oh.
By removing these limitations of having to process things in a sequence, it unlocked the potential for much richer representations of language.
Can you give me an example of that?
Think about it this way. Instead of just seeing like a list of words, the model can now understand this whole web of relationships. You know,
yeah.
it can grasp the meaning in a way that's much more, I don't know, human-like.
That's a great way to put it.
Yeah.
Do you think the authors knew that they were onto something this big? Like, did they realize that they were creating this blueprint for this whole new era of AI?
It's hard to say for sure, but I think there are these little hints in the paper that they knew they were onto something.
Okay.
You know, they talk about being really excited about the future of attention-based models and how they want to apply these ideas to other things like analyzing images and audio. It's like they planted a seed, and that seed grew into this whole forest of different AI applications.
I love that analogy. It's amazing to think about how one paper can have such a ripple effect. It really speaks to the power of human ingenuity and collaboration.
Yeah, definitely.
Speaking of collaboration, there are 8 authors on this paper. Do we know anything about how they worked together? Was there a clear leader, or was it more of a team effort?
That's a really great question. And, you know, the paper actually gives us a little bit of insight into that. It says all the authors contributed equally, And the order they're listed in is totally random.
Oh, interesting.
But they do give a shout out to one of the authors, Jacob, for suggesting the idea of swapping out RNNs for self-attention, which is what really got the ball rolling. So even though it sounds like Jacob had that initial spark, it really took the whole team working together to make it happen.
That's really cool to see how they work together. And it's a great reminder that sometimes it's not about the lone genius. A lot of the time, it takes a talented team to make these big breakthroughs happen. So we talked about all the technical stuff, but I'm also really interested in the practical side of things. We talked about machine translation, but what other cool things have come out of this research?
Oh man, where do we even begin? The impact has been huge. It's not just about translating languages anymore. It's about really understanding and generating human language, like in all its complexity.
Right.
One area where it's made a huge difference is in natural language processing, or NLP, as we call it. Think about chatbots, for example.
Okay, yeah.
Before the transformer, most chatbots were pretty basic, like they just followed these pre-programmed scripts.
Right, they were pretty limited.
Yeah, but now, thanks to the transformer, we have these chatbots that can understand and respond to you in a way that's much more nuanced, much more sophisticated.
So those chatbots that seem so real, like the ones where you almost forget you're talking to a machine,
Yeah,
those are powered by transformers.
exactly.
Yeah.
They can understand what you're saying, they can be creative, and they can even adapt to how you talk, like your own personal style. It's almost like you're having a conversation with a digital version of yourself,
That's wild.
or at least a version that's been studying your every word.
Yeah, a little creepy, but also really cool.
But it goes beyond chatbots.
Okay.
Transformers have also revolutionized what we call language models. These are models that can, write different kinds of creative text formats like poems, codes, scripts, musical pieces, email, letters, etc. They can translate languages, and they can answer your questions in a really informative way, even if you ask them something really open-ended or strange.
I've seen some of those in action, and it's pretty mind-blowing. They can write stories, compose poems, generate code. It's like they've tapped into this creative force within the digital world.
Yeah, it really makes you wonder, what does it even mean to be creative? Is there a difference between what humans do and what these machines can do?
It's a big philosophical question for sure.
Yeah.
But it's also important to think about the practical implications. Like, imagine a future where you could have a personalized news article written just for you, or a virtual assistant that can write emails and reports, even novels based on your ideas.
It's like having Shakespeare on speed dial, ready to whip up whatever you need. The possibilities are endless. But we also have to talk about the potential downsides. Any technology this powerful has the risk of being misused.
Yeah, that's a good point. What are some of the ethical concerns that we should be thinking about?
We have to think about how these technologies could be used for things that could cause harm.
Yeah, like what?
What if these language models are used to create fake news articles that are so convincing nobody can tell they're not real?
That's scary.
Or imagine deepfakes, videos that are manipulated to make it look like someone's saying or doing things they never did.
Right.
If they become so realistic that we can't tell the difference between real and fake, that could have serious consequences.
It really highlights how important it is to use these tools responsibly and to make sure people understand how they work. We need to be more careful than ever about the information we consume and think critically about what we see and hear, especially online.
I couldn't agree more. It's a shared responsibility to make sure these powerful technologies are used for good. Attention is all you need. Opened up this whole world of possibilities. But it's up to us to navigate it wisely.
Well said. So before we move on to our final thoughts, I want to zoom in on something specific from the paper.
Okay.
I noticed that they talk about positional encodings.
Yeah.
What are those, and why are they so important in this whole transformer thing?
You've hit on a really key detail there.
Okay, good.
Positional encodings are basically the transformer's way of keeping track of the order of words in a sentence.
Oh, okay. Because it doesn't process words one at a time, like those old RNNs, right?
Right, exactly.
So how does it know which word comes first, which one comes second, and so on? If it just sees all the words at once, it'd be like reading a sentence with all the words jumbled up. You'd lose all the meaning.
Exactly. And that's where these positional encodings come in. They give the model information about the order of the words, even though it's looking at the whole sentence simultaneously.
So how do they do that? Do they give each word a number, like a timestamp or something?
It's a little more clever than that. They use these special functions called sine and cosine functions.
Sine and cosine. That sounds like high school trigonometry.
It does, right?
What do those have to do with language?
It might seem strange, but those functions, They have these properties that make them really good for representing position.
Okay,
Each position gets its own unique code.
got it.
And these codes, they get added to the word's representation so the model can see where the word is in the sentence.
So it's like each word has a little flag saying, hey, I'm the third word in this sentence, or I'm the 10th word, or whatever.
That's a great way to put it. And because of these positional encodings, the transformer can make sense of the order of words, even though it's processing them all at once.
That's a really clever solution to a problem that could have been a major roadblock for the whole thing.
It really is.
It's amazing how these authors thought of everything. Did they try any other ways to represent the position of words?
Yeah, they did actually. In the paper, they mentioned that they played around with what they call learned positional embeddings. It's similar to how the model learns to represent the words themselves.
Okay, so instead of using these sine and cosine functions, they tried to let the model figure out its own way of representing word order.
Exactly. But they found that both ways, using the fixed positional encoding with sine and cosine, and then this other way of letting the model learn it, they both worked pretty much the same.
So they went with the simpler approach, the one that didn't require any extra training.
You got it. They chose sine and cosine because it was more efficient and because it might let the model handle even longer sentences than what it saw during training.
Oh, that's smart. But why is that sine and cosine method better for handling these longer sentences?
It has to do with how those functions work.
Okay.
Sine and cosine, they're these waves that repeat over a certain interval.
Okay.
So the model might be able to see patterns and then keep going, even beyond what it was trained on.
So it's like the model is learning a rhythm or a tune that it can just keep playing.
I love that.
It's fascinating how something as complex as the order of words can be represented by these mathematical concepts.
It really is. And it shows how we can use these elegant math ideas to capture even the most abstract linguistic features. I think it's about time we wrap up this part of our deep dive. We've talked about attention, these positional encodings. It's been a lot.
Yeah, we've definitely covered a lot of ground. But before we move on to our final thoughts, I want to turn it over to you, our listener.
Okay, good idea.
What do you think is the most significant contribution of attention is all you need?
Yeah.
Was it the transformer itself? Was it the emphasis on attention? Or was it something else entirely?
It's a tough question.
It's a lot to think about. We're going to take a quick break, and then when we come back, we'll share our thoughts and try to answer that question together.
Yeah, it's always amazing to see what people take away from these papers. When they really get in there and think about the impact. There's just so much to consider, and it's all had this huge effect on AI. But before we go too far down that rabbit hole, there's one more thing from the paper that I think is worth talking about.
Okay, what's that?
You know how we talked about attention?
Yeah.
And how it lets the model focus on the important parts of a sentence?
Right.
Well, they actually get into the nitty-gritty of the specific type of attention they used. It's called scaled dot product attention.
Oh, yeah, scale dot product attention.
And if I'm being honest, the math behind it was a little over my head.
Yeah, you get a little hairy.
Can you break it down for us? Like, explain it in a way that makes sense, even to someone who's not a math whiz.
Sure, I think I could do that. So imagine you have a question about a sentence, something you want to figure out.
And that's your query. And then you have all this information, like pieces of a puzzle, that might help you answer that question. Those are your keys and your values.
So the query is like, I don't know, what's the main idea of this sentence?
Exactly.
And the keys and values are like clues the model can use to find the answer.
You got it. Now, scaled dot product attention is all about finding the best match between your query and all those keys. It gives each key a score based on how well it lines up with the query.
So it's kind of like a matching game, finding the most relevant information to answer the question.
Exactly. And the dot product part is just the math they use to calculate those scores. It involves multiplying the numbers that represent the query and each key. The higher the number, the better the match.
Okay, I'm starting to get it. But what about the scaled part? What's being scaled?
So they scale the scores down by a certain amount to make sure they don't get too big. It's like adjusting the volume so things don't get too loud and distorted.
Okay, so it's like fine-tuning the matching process.
Yeah, exactly. And that's what makes scaled dot product attention so powerful. It helps the model zero in on the really important connections without getting distracted by all the noise.
Wow, they really put a lot of thought into this. It's this perfect mix of like math and intuition about how language works.
I know, it's amazing, right? They really understood what they were doing. And they weren't just throwing equations around. They created a system that could actually grasp how nuanced and complex human language is. And that's inspired so many other researchers to follow in their footsteps.
It shows how innovation can come from, combining expertise with this spark of creativity. It's
Right.
about understanding the problem and then finding these elegant solutions. And in this case, they didn't just solve a technical problem. They came up with this whole new way of thinking about language processing. They showed us that attention, this thing that we do naturally as humans, could be the key to helping machines understand and generate language, like on a whole other level.
And the craziest part is it worked.
It did.
And it worked incredibly well.
This paper, attention is all you need. I mean, it's more than just a paper at this point. It's like this landmark achievement that changed the course of AI.
It really did. I mean, think about it. The transformer, with its attention mechanisms, it's become the foundation for so many incredible advances. We've got chatbots that can hold these nuanced conversations. We have language models that can write, translate, and answer questions in a way that's, almost human.
Yeah, it's mind-blowing. And all of this came from this one paper. It's really inspiring to think about the impact that research can have, how one idea can spark this wave of innovation that changes the world.
Yeah.
But as we wrap up this deep dive, I think it's important to remember that we're still in the early stages of this AI revolution.
We are, definitely.
There's still so much to explore and discover, and it's up to all of us to make sure that these powerful tools are used for good, that they benefit humanity as a whole. Attention is all you need. Give us a glimpse of what's possible. But the future is still being written.
It's true. And it's being written by all of us. Researchers, developers, policymakers, everyday users. We all have a part to play in shaping this future. So stay curious, ask questions, and keep pushing the boundaries of what we think is possible with AI. Because who knows what amazing discoveries are waiting for us just around the corner.
That's a great note to end on. Thanks for joining us on this deep dive.
Yeah, thanks for having me. It's been fun.
And to our listeners, thanks for tuning in. We'll see you next time for another deep dive into the world of AI.